So in this video, we're going to go ahead and talk about how to solve quadratic equations. And this is where we really start to get into some Algebra 2 processes. Because unlike in geometry and Algebra 1, the process to solve, though it does use reversing Gelmdas as the other processes, there are some decisions that have to be made on how to handle the upper steps of this process. So just like always, we're going to simplify by going from the grouping symbol, the exponent, multiplication, division, addition, subtraction. Then we're going to solve by starting at the bottom. We're going to add or subtract things to get the equation in the right form. We're going to multiply or divide things to get the equation into the right form. We're going to eliminate the exponent, and with quadratics, that's predominantly done by factoring, though there is a way to take a square root at certain times. Then if there's anything on the inside of the grouping symbol that hasn't been taken care of, you start at the bottom and go back through again. So let's take a look at the first two methods. They will seem very familiar to students. So the first method is what is known as the square root method. It's really the process you're used to seeing with reverse Gelmdas. So this is very simple. What you do for this method is, first thing you want to notice is, does the equation have this term? So you put it in this standard form. And if this term is missing, that's how you know you have the square root method. Notice this, see how it's not here? And over here, you would not get that term unless you squared it out. But you don't want to square this term because you're trying to solve it. And the way you undo this would be to take a square root. So let's go ahead and look at the process. So we're going to start with the bottom of Gelmdas, which is to add or subtract. So we're going to subtract the 7 right here to both sides. That will now give us 5x squared is equal to 2. Okay, and then we've done the addition or subtraction step, so we're now going to do the division step. Right, so then we just have this little fraction, and then our last step will be to deal with the exponents. There is no grouping symbol. You can see there is one on the next problem. And so the way that we deal with that exponent is we take the square root. So if I take the square root, it will eliminate the square. Remember, the reason that is the square root is really 1/2, and so if you were to surround this in a 1/2, the 1/2 and the 2 multiply and give you x to the first power. And the question is, what do we do over here? Well, two things we have to remember. When we take the square root, don't forget there's always a plus or minus. Always, 100% of the time. If you write a square root on a problem to solve it, it creates a plus or minus. But when you take the square root, there's actually a square root on the top and the bottom. Now, why is that significant? Because we have to follow all of the rules that we have seen in the past. So the square root on the top is fine, but when I have the square root of 5 on the bottom here, we've learned in geometry and in Algebra 1 and in this course that square roots on the bottom have to be rationalized. So I'm going to come back and I'm going to rationalize this by multiplying by the square root of 5, and that will give me my final answer. So the final answer to this problem is plus or minus the square root of 10 over 5, which is the exact same answer as the square root of 2/5, but this one has been rationalized. And you can, in fact, go and store this and put this in here and square everything, and it will say it's equal to 9 with either the plus or the minus. So it does work, and it does work with the minus. And the reason the minus works is because you end up squaring it, and that will make it positive. So let's take a look at this one. So on this one, we're going to be reversing the Gelmdas process from the bottom. So add or subtract. In this case, we're going to subtract. And when we subtract that, we end up with everything dropping down. Should feel very familiar to you based on other units that we've already seen. All right, and so this will cancel, and this will equal 8. So the next step will be to divide by 2. Canceling it here. Remember, you cannot distribute this in here. This is not possible because it doesn't have the same exponent, right? Remember the rules for exponents. You have to have the same base or exponent to combine those. That does not have the same base or exponent, so that's impossible. So we divide this by 2, drop this part down. This will equal 4, and then we take the square root, just like we did over here. So we take the square root of both sides. Don't forget to immediately put a plus or minus on it. So now we have x plus 5. And then here we have, and this is interesting, the square root of 4 is actually an integer. It's plus or minus 2. So to solve this part of the problem, it's going to look a lot like the absolute value. where we're actually going to set up two problems, one being positive and one being negative. So x plus 5 is equal to 2, and then we also have x plus 5 is equal to negative 2. So you see that when I solve problems, I just try to keep them as consistent as possible. And what you're seeing there should look very similar to other things that we've seen in the course. If you went back and looked at the video on how to solve absolute values, it looks very similar. Though we're not solving an absolute value problem, we are using a process that we established at the very beginning of the year. So here we get x is equal to negative 3. And here we get x is equal to negative 7. And so this will be a much easier way to show you how to check, just like in before. You're going to take the negative 3 and plug it into here. So if this were negative 3, this expression would be 2. 2 squared would be 4. 4 times 2 is 8. 8 plus 6 is 14. So that does check. If I put negative 7 in there instead, right? So if I were to put negative 7 in there, a very similar thing will happen. Okay, so if I put negative 7 right here, I end up getting negative 2. But when I square it, it's back to positive 4. 4 times 2 is 8. 8 plus 6 is 14. So they both work. And keep in mind that this could be written like this, right? A lot of times on standardized tests, they organize these, and they're organized in ascending order, just like with domain and range. So the negative 7 would come first. All right, so that should feel very familiar. Let's take a look at another process that if you've taken Algebra 1, and if you had a geometry teacher that prepared you for an advanced class, you would have solved quadratics like this as well, even with shapes and geometry. So the second method is the factoring method using the zero product property. And don't be scared of the zero product property. You have seen it before, you just maybe didn't know its name. Here's what the zero product property says. If a times b equals 0, then a equals b or b, sorry, let me say that again. If a times b equals 0, then a equals 0 or b equals 0, or both of them equal 0. And we'll see that in action in just a second. So here's the process for how to solve a quadratic equation that has, notice that these have this term that the other ones did not. So when I go and look at the other ones up here, they don't have that term, and that's the key difference. So what happens? What's the difference in what we do? Well, what we do here is we are simply going to take these terms and we're going to move them over to the other side using the bottom of Gelnbath. So I'm using the addition and subtraction step right now, right, to clean this up just like we normally would. Over here, these are set, these are canceled, and the problem is set equal to 0. The reason we're doing that is we're trying to use the zero product property. Over here, what will happen is these will combine, and then we're at this stage. Now, what we have done is we've added or subtracted. There is nothing to multiply or divide. You can tell that because there's nothing in common. All right, so now what do? Well, we get rid of the square by factoring, because the factoring process eliminates the exponent, and that's why we factor. So the way you factor is if you have a minus, you always have an x plus and an x minus all the time. 12 has 3 terms, 1 times 12, 2 times 6, and 3 times 4. And so this is the question you ask yourself. Okay, these are the factors, the different ways you can multiply to get 12. This is a subtraction problem. So you ask yourself, in which way can I subtract these factors to get 1? Is it 12 and 1? Nope. That's going to give you 11 or negative 11. Is it 2 and 6? No, that's going to give you 4 or negative 4. But 3 and 4, if I subtract them in the right order, will give me negative 1. And the order would be to subtract 3 and then minus 4, because 3 minus 4 is negative 1, and 3 times negative 4 is negative 12. Now I will use the zero product property. Notice here I have a product. These are being multiplied. So I set them equal to 0 because the zero product property allows me to. And then I solve these two terms for their x variable. So this one would be negative 3. You don't have to show work on a problem that easy. This one would be 4. And what happens is if I put these back into the equation, they will create balance. Let me show you what I mean. If I take negative 3 and I put it here, I would get 9. And if I put negative 3 here, I would get negative 9. So this side of the equation equals 0. And if I put negative 3 here, I would get negative 12 and then plus 12. So that also produces 0. So that checks out. And if I did it with this one, if I put 4 in here, I would get, let me erase this previous check here. So if I were to put 4 in there, what I would get is I would get a very similar situation. I would get different numbers though, right? So here, if I put 4 in here, I would get 16 and then plus 12, right? 4 squared, 3 times 4. So this would be 28. And if I put 4 here, notice what I get, 16 plus 12. So again, I get 28. So those both check out, and please keep in mind that they could be written in this format. They could be written as -3, 4. All right, so let's take a look at this next one, very similar process. Again, so notice, the most important thing you notice is that these have the bx term. Unlike these, right, see, there's no x. There's just this x squared. Here, this is in a parenthesis, so it's x squared, and you would not get the bx term unless you FOILed, and you don't want to FOIL or use the box method because it'll create more work. So let's go down and take a look at how to solve this. So we notice that it has that bx term. Our goal now is to set the problem equal to 0 to use the zero product property. And the zero product property is pretty much used in all of math above this lesson. We'll be using the zero product property in every unit. So then this will now become 3x squared minus x minus 4 equals 0. And now we have a problem here. These cancel out. That equals 0, but it does not have a lead coefficient that is simple like this one. It has a 1. So what do? Believe it or not, you can actually use the box method in reverse, and that's why I focused on it so much. It's a great way to do this. So what we're going to do is we are going to try to get the outside factors here and here by knowing these numbers. So the first thing we do is realize that the 3x has to be 3x times x. And again, that produces 3x squared. So in effect, we have checked off this part. That part's done. So now the next thing we have to do is we have to understand that this is a minus. So our next thing in our factors has to be plus minus, just like it was here. So how do we do that? Well, we have two choices. We have 1 times 4, and we have 2 times 2. And you just sort of have to plug them in and see if you get the correct middle term. Because if I put a 1 and a 4 here, I know I've got 4, but the question is, do I have -1? So let's see what happens. If I put the 4 here, I get 4x. And if I put the 3x times 1, I get 3x. One of these has to be negative. So it's very similar to this process. Over here, we were asking, well, I got to subtract. But here I actually have my variables. So, and you can actually use the box method to do these coefficient 1 problems. So I need a negative. To get -1, I would put the negative right there, which means the negative was actually, you have to go outside now. So now if I combine these like terms, I do in fact get -x. So I've checked off all my boxes. I just got to arrange my negative signs. So this negative that I added, since I was multiplying, was actually here, and we did make this negative. So now that now checks out. So your factors are up here. There are your factors. So you get x plus 1, and you get 3x minus 4. And if that didn't work, I actually just got lucky and put it in the right place that time. Let's say I would have put the 1 here and the 4 there. The 3 here and the 4 there. It wouldn't have worked, and I would just erased it and then try to reverse it and see if it worked. And if that didn't work, I would try the 2 and the 2. But now I'm going to do the zero product property to get my other answers. So x plus 1 is going to equal 0. That's simple enough to just put the subtract in my brain. And then here I'll have 3x minus 4 equals 0. Again, that is the zero product property saying that A or B equals 0 in a product equaling 0. I'm going to add 4 to both sides here, and then I will divide by 3. And it is possible that this will reduce, but in this case it does not. So here are my two answers. With 4/3, I would probably want to use either a calculator or Desmos to check that one. And you would check it the same way. You would just take these two answers separately, one at a time, and put them in here. We can easily check -1. If I put -1 in here, I would get -3 minus 3, which is 0. And here I would get -4 plus 4, which is also 0. So you can definitely see that we're on the right track. To check 4/3, I'd probably want to use Desmos. All right, so now that we've completed how to do quadratic equations in a more traditional way using reverse Gelndas, it's important to understand that when we get to quadratic equations, we have this formula, this famous formula called the quadratic equation. And the question is, well, why do we need it? Well, sometimes problems don't factor, nor do they use the square root method. So we would use the quadratic formula when the square root method is inappropriate, meaning you have a bx term, because if you have a bx term, you need to factor. But if you have that bx term and it doesn't factor, this formula will provide an answer, though a very unattractive and kind of messy answer. And it's typically used for science, engineering, or other application problems. So within the formula, there's a really special part of it right here, okay, called the discriminant, and it is used to determine the number and type of solutions. What that means is it'll explain to you how many answers you have and whether or not they will be real or complex. So before we start doing any problems, let's take a look at what the discriminant actually does. So it is used to determine the nature of the roots. That's a Virginia SOL term that's typically used. And so if the discriminant is greater than 0, meaning if it's positive, so if you do b squared minus 4ac and it comes out to a positive number, there's always going to be 2 real solutions. And what that means is that if I look at the graph, it's going to cross the x-axis twice. Okay, the graph could also go down like this and cross the x-axis twice, but generally it means that there are 2 answers crossing the x-axis. If the discriminant, if b squared minus 4ac is less than 0, otherwise known as negative, and I included this in our notes because on the SAT, they don't say something is positive or negative. They say it's greater than 0 or less than 0. So if the discriminant is negative, there will be 2 complex solutions. Notice the graph does not cross the x-axis at all. Here's the x-axis. Notice the graph is below it. The graph could also be above it up here, and it can cross the y-axis. In fact, every function will cross the y-axis. But it's not crossing the x-axis at all. And the third case is what happens if it actually is equal to 0, so neither positive nor negative, but equal to 0. That means that it's going to cross, that means it's going to have one real solution. It's going to cross the x-axis one time right here. And you can remember from previous chapters, that means that the vertex is on the x-axis. Keep in mind it could be going downward like this, right? And that could be here, so it could be a reflected graph, but it will still have one answer. All right, so that's a great place to pause and take notes on what we had. So I would take notes here, and then I would take notes here. Oh, one last thing. So the discriminant, if it is a perfect square, so let's say you do the discriminant, all right, and it comes out to a perfect square, meaning 0, 1, 4, 9, 16, 25, 36, anything like that. That actually means the problem is factorable. And why that's important is you might be on a test, and you might be trying to do the quadratic equation, and then you do the discriminant first, because I always teach you to do it first, and you end up getting 81. What you would do there is probably stop and then factor it, because the quadratic formula is kind of foreboding. All right, so I would stop, and I would take notes. All right, let's take a look at an example using the quadratic formula. And the first thing you'll notice when you see this problem is it looks like all other quadratics. But notice that here's the process to think through. This has a bx term, so we can't use the square root method. So I would try to factor it, and the factors of 4 from multiplication tables are 1 times 4 and 2 times 2. And these factors do not subtract to give you 2. That's impossible. So that's when you would use the quadratic formula. So we start by using the discriminant, b squared minus 4ac. To do that, we want to make sure that we label properly. It's very easy to get confused. The quadratic formula can at times seem vague. So you want to label. A in this case is 1. It is not 1x squared, it's just 1. It's the coefficients. B would be 2. And C is negative 4. So we're going to put those into the discriminant, and we're going to see what number pops out. So here we have 2 squared minus 4 times 1 times negative 4. And many times you can use a calculator for this, but these are small enough. So let's take a look at how to do this by hand. This would be 4. These 2 negative signs would make a positive sign. and 4 times 1 times 4 is 16, so this comes out to 20. So what does that number mean? Well, it is part of the answer, but before we get to the answer, if we go back and look at this portion of our notes, it tells us that it is positive, and positive will produce 2 real solutions and 2 x-intercepts. So it's important to know that this will produce 2 real solutions, okay, and those real solutions will also be 2 x-intercepts. All right, so this is a strange thing for students to see because it's an answer that provides this explanation. So the actual numerical answer is to use the quadratic formula, but watch what's so great about having this. I'm going to have minus b and then plus or minus the square root of b squared minus 4ac, but I don't need to write b squared minus 4ac down because I know that it's already 20. Like I already know that that's what it is. And then I'm going to divide that by 2 times a, right? And so I'm going to go back to my labeled numbers up here. I have 2. It's actually going to be negative 2. It's good to put things in parentheses when you substitute. And then plus or minus 20, which I'm going to go ahead and break down since you want to break things down as soon as you can. And you'll notice by doing this why I taught things in the order that I taught them. Because we already learned this skill in the last chapter, and now we're using it in the middle of the problem. So that'll come out to 2 root 5. So instead of being a problem in its own, it's now part of the simplification process. And then down here we have 2 times 1 because a was 1. So now I'm going to simplify that. So x is going to be negative 2 plus or minus 2 root 5. These are always square roots. We will not be solving any cube problems with the formula. The formula, it does exist, believe it or not, but there's really no point. We're going to learn different processes when we get to the cube chapter. So we're now going to use another skill that we learned just in the other chapter, and actually in Unit 1 and Unit 2, which is to factor out a common term to reduce this. Can you reduce it by dividing? The answer is yes, but typically mistakes are made and a lot of errors can come that way. And factoring using GCFs is such a great way to understand how the reducing process works. So we end up getting that x is equal to negative 1 plus or minus the square root of 5. And the question is, well, what in the world does that mean? Well, this answer can be broken up, and I used a calculator this time. I'll use Desmos on the next example, but I just, if you have a Casio or a TI, you can type in negative 1 plus the square root of 5 and get 1.236 and some other numbers. And then if you do negative 1 minus the square root of 5, you get negative 3.236 and some numbers. And now what do those numbers mean? Well, we know that those are the real solutions. There's no imaginary, but they actually mean that there are 2 x-intercepts. And if I take a look at the graph, you can graph this on the TI by going to y equals and graph, or on the Casio by going to the main menu. And I find the 0, which on the Casio would be a root. Notice that this number that it found is the same as the negative answer. And then this number here, I have to do it again on the calculator. This number that I found is the same as this number. And so you can see what those numbers mean. They start out like this, and they end up looking like this, meaning they're actually x-intercepts. So this number here is the positive x-intercept, negative 1 plus the square root of 5, comma 0 is this answer right here. And then the negative 1, which is over here, is negative 1 minus the square root of 5, comma 0. And that's what they would look like as x-intercepts in, in the math form. These irrational numbers that come out from the calculator, they make a little bit more sense. You can see it's a little bit beyond negative 3, a little bit beyond 1. All right, let's take a look at the second example, and I purposely made this one not as obviously non-factorable. So this one, it's obvious that it's not the square root method. It's obvious it doesn't factor. This one, it's also not already in the zero product property form. We got to put it in that form. It's a little bit more involved. So we're going to start by zeroing it out. And one of the things we need to remember just consistently about quadratics is we want the lead coefficient to be positive. We don't want to move these things over here. Even if there's more work to leave this positive, you want to leave it positive. So I'm going to subtract the 14x, and I'm going to add the 40 to their corresponding like terms on the other side. And then I'm going to make sure that I carefully balance this equation, because this equation at this point, if I'm not careful here, all the steps after this will not be correct. And there's nothing more frustrating for a teacher than a student who you want to do well that forgets to combine these like terms, and they make the problem harder than they need to, or they go through the entire quadratic formula, do everything right, and the only mistake they made was here. So just be careful that you actually combine like terms and take a second and check your work. So it's clearly not obvious if this factors. If I were taking a test, I might try to take the 2 out by GCFing it. Then you would find that you have an 8, and over here you have a 20, which that is close to factoring but doesn't actually work. So if you're ever just lost on a test and you're like, I don't know if it factors, if you do the discriminant, remember the discriminant can help you. Again, it's a good time to maybe make sure you wrote down this statement about the discriminant needing to be a perfect square. And this example is actually really interesting about how that works. So in here, it's good to label. So this is A, B, and C. Okay, and so we're just going to plug these numbers in here. We have negative 16 squared minus 4 times 2 times 40 is C. And keep in mind here that you want to check this. I mean, if you accidentally put one of these in the wrong place, it doesn't work. I mean, it's a formula. It has to be done precisely. And that's way too much information to try to do in your head or on a calculator. I mean, without a calculator. So I'm going to use Desmos. And as you can see, I typed it in. To do this, you got to make sure that you hit Shift 6 or use the caret, and then you use the right arrow key to get back down here. And you can see that we get negative 64. So I'll snip that, throw that in our notes. The reason that that's a really good thing to have, okay, is that answer, I picked this problem purposefully, is because of the fact that looks like a perfect square. You get negative 64. However, negative 64 is not a perfect square because one of the numbers would have to be positive and one of the numbers would have to be negative to give a negative. And a perfect square means they're identical. So negative 8 and 8, they're not identical. So what that tells us is it tells us that there are two complex answers. Complex meaning part of it is imaginary. So two complex answers are solutions. It also tells us we have no x-intercepts. And the reason that's so important is it is possible on an SAT or an SOL even, to have a question that says, which of the following quadratics has no x-intercepts? They're not actually asking you to graph it. They're asking you to use a discriminant and look for discriminant values being negative. All right, let's run through the whole quadratic equation now. So x is going to be equal to minus b, so that would be minus 16, right? And then plus or minus the square root of negative 64, and then all divided by 2 times a, which is 2. So let's do the easy parts first. Negative is 16. If you want to just put that in as 16 in the first step, that's fine. The denominator is 4. And now we have to remember, again, you'll start to understand why I teach things in the order I do. I teach them so they're connected to concepts that directly follow. We talked about this in Unit 2, that if you take the square root of a negative, that's actually I. And we reinforce that at the beginning of this unit in when we talked about complex numbers. Now, the square root of 64, you don't have to make a tree for it. The square root of 64 is, in fact, 8, and we typically put that 8 in front of the I because the I is a variable that's special, as we learned in the beginning of this class, this section. So now we're going to factor this by removing the common 4. Notice that this is the denominator, and there's a 4 in the top on both factors. This is, again, a situation that we've seen in previous chapters to factor this out like this by finding the greatest common factor. The bottom is 4 times 1, so it will cancel. And so x is equal to 4, the real part, plus and minus 2i, the imaginary part, making this complex. So what does that answer mean? Over here we looked at a graph, and I'll look at this one on Desmos. We did the calculator on the other one. So in here, if I type in, you always have to type in the zeroed out part. And you have to say y equals, or else it'll try to do some other things with it. And then again, you go down, minus 16x, and then plus 40. You can see that the graph appears above the x-axis. All right, and that is a great thing to see because what you'll notice by doing it this way is that it correlates directly with those notes. And that's why, it's important. I know you're watching a video right now, but it is important to take notes so that your brain can process this a little bit better long term. So I want you to just take a mental screenshot of that. I'm going to go back and look at these notes right here. That's exactly this example. So that's exactly this, right? We had a negative discriminant. There are two complex solutions. It did not cross the x-axis. Now in this example, as I mentioned earlier, it's going up rather than down, but it's the same exact situation. Our fourth and final method for completing quadratics is completing the square. Please keep in mind that you're really mainly going to use method 1 and 2, which is factor, or use the square root method. And believe it or not, the one that kids forget the most is the square root method, which is the easiest. So important things to remember about completing the square. A completed square is a quadratic expression that factors in the pattern a squared plus 2ab plus b squared, or minus 2ab, and then again this would be positive, and the factors come out to either be double positive or double negative. So an example of that for you to look at would be if I had x squared minus 10x and then plus 25, notice that this number is a perfect square, right? And it's a perfect square of 5 times 5. So the factorization of this will come out to x minus 5, because the middle term is negative, and then x minus 5 again, right, because that's the identical twin term, making it a completed square. Negative 5 times negative 5 is 25, but when I add these two terms together, I get negative 10. And interestingly enough, completing the square is the universal method to solve quadratics. It will solve any of them, but you don't want to do the most difficult process to solve the easiest problem. Again, we're going to focus mainly on assessments on method 1 and 2, with a few of quadratic formula and completing the square on an assessment. In fact, the mathematical proof for the quadratic formula is made using completing the square. There are plenty of videos on YouTube if you want to look at them to see how that works. It's not something you'll be assessed on at any time. That's just interesting for those kids who want to see it. Completing the square can also be used to rewrite a quadratic function from standard form into vertex form, meaning you can take an equation that's in this form and rewrite it using the form from Unit 2 for transformation of functions. So that's another very important use for it, which is used a lot in upper level math. So let's take a look at how to actually just complete the square. So let's say I had this problem, and I wanted to figure out a c value that would give me an identical twin number that would add to 2. And I tried to make it easy there. That would make c equal to 1. And 1 is the perfect square that students forget a lot. So if that were the case, I would have x squared plus 2x plus 1. And that would factor into x plus 1 and then x plus 1 again. 1 times 1 would be 1, and 1 plus 1 would be 2. So let's see if we think about this one, right? So I need to think of a number that's going to add up, that's an identical twin of 8. Sorry, that will add up to 8 as an identical twin. That would be 4. But if I square it, because it has to be squared, it would be 16. And the reason it has to be squared is because we're talking about a quadratic. And so if I rewrite that expression using that, I have x squared minus 8x plus 16. And that would factor into x, be careful here, minus 4, because the middle term is negative, and then x minus 4. Those are your identical twin factors. Now, very useful later, since we looked at the first two, would be to actually rewrite this as x minus 4 squared, because there are two of them, and this one would be x plus 1 squared, and that's actually where it gets its name. I want to show you two examples first. So let's think of this one. What numbers would have to be identical twins to add up to negative 18? That would be negative 9 and negative 9, but when I multiply this together or square them, I would get 81. And so the expression would turn out to be x squared minus 18x plus 81, okay? But then the factorization would be x minus 9. Again, why are they negative and the first one was positive? Because of the middle term. That one's positive. These two are both negative. So my expressions will be negative, and this would be x minus 9 squared. So then we get to one that's a little bit harder. And so that's when we start to come up with, well, how did we actually do these? The way we did these is we took half of this number, right? And then we multiplied it times itself, otherwise known as squaring it. And so when you get to a one like this, it's like, what number do we add together plus an identical twin to get 5? We really need this little mnemonic key device here, which is to do half of b, so b over 2, and square it, and that will always make a completed square. Half of 2 is 1, 1 squared is 1, half of negative 8 is negative 4, squared is 16, half of negative 18 squared is 81, half of 5 is 5 halves squared, which would actually come out to 25 fourths. And I know that may look a little scary at first, but it's just a number we need to write down because we know what the factorization is going to be. The factorization is always half of b. So even though we write this down and we're like, wow, that's a pretty intimidating looking expression, right? This expression right here is pretty intimidating. We don't have to really worry about what c is because we know that the factorization is always going to be half of b, so 5 halves. And you do not want to do this with decimals. You'll see more why when we solve problems. And so this expression would come out to x plus 5 halves squared. So now that we've seen how to make a perfect square, let's go over the steps of how to actually use it to solve something. And this is where we'd really want to take some notes. So step-by-step instructions for solving a completed square to solve an equation. First thing you're going to do is rewrite the equation into ax squared plus bx equals c. You actually want the constant over here and not 0. So if you set it equal to 0, you can just move it over. You're always going to factor out an a if a does not equal 1. That is extremely important, and you'll see an example of that in just a minute. If you don't, the equation won't be balanced, and obviously if an equation is not balanced, it can't be correct. The next thing you're going to do is calculate b over 2 squared. That was the whole purpose of this. If you wonder what was the purpose of this, is to help you understand why we need b over 2 squared. And then add it to both sides to balance the equation. You're going to rewrite the problem as a perfect square using b over 2 to factor the left side. That's what we did here. So that's this step. Okay. Then you're going to use method 1, the square root method, to solve for x. Because if they're all squared, we can get rid of that in an equation by square rooting. And that's the process. So I would write down these steps, rewrite this, factor, calculate. I'll give you a second to do that, and we'll look at some examples. All right, so these examples are the same ones we solved just a couple of minutes ago with the quadratic formula. I like to show them to you get the same answer, and also to show you that maybe completing the square is an easier way in some instances. So in this problem, again, it doesn't factor 1 times 4. If we have 1 times 4 and we have 2 times 2, there's no way we can get 2 by subtracting them. That's how you think about factoring. So we are going to use the completing the square method. Completing the square method using step 1 is to actually use that number on this side because we need to solve an equation. And I actually put a little blank there because we're going to hold the place value for what the completed square is. And you'll notice what I did there. This side of the equation right here is exactly the same, right, as this example we did here. I mean, it's the same problem as this. That blank is the c. All right, so the same number we used here, we used 1, we're going to put right there. So we put a 1 here because 2, right, we're going to do b over 2 squared. Right, so in this case it would be 2 over 2 squared would be 1. So we'll put a 1 there, and then we'll add 1 over there to balance the equation. So here we'll have x plus 2, x plus 1 is equal to 5. This is a perfect factorization of x plus 1 equals 5. This will then factor into x plus 1 squared, and that equals 5. And now we're going to solve it using the square root method, which would be to square root both sides. Don't forget your plus or minus over here. So as soon as you put a square root in a solving problem, it has a plus or minus. So these will cancel. They actually inverse. So x plus 1 is equal to plus or minus the square root of 5. And then using reverse Gelndas, we will subtract 1 on both sides, and you'll get the exact same answer as you did with the quadratic equation. You get -1 plus or minus the square root of 5. So let's go back and look at that example. So taking a look at the second example here, notice that it's not already set up for 0. It's just like the one we did earlier when we did the quadratic equation. So we're going to want to start by setting it equal to 0, zeroing out, as some people will say. Just make sure, again, that you're careful with your like terms. All right, so add this over here. And, one of the most important things you do, because when you do this process right here, again, it's really important to make sure that this lead coefficient is positive. So when you zero this out and you set this equal to 0, if you have a lead coefficient that is negative, that's a bad thing, just in general for quadratics throughout the whole chapter. Make sure you combine your like terms, as we mentioned on the previous example, and make sure that you haven't made a boo-boo at the beginning. All right, so now what we're going to do is we're now going to, doing this process, you would say, okay, well, it doesn't factor, I want to complete the square. You would actually move the 40 back over here, and just make sure when you do that, that you make sure that it is negative, right? It's a negative 40. When you get a little better, you might just leave this term here, right, and then move forward with it. But, on a test or something, I will probably label the problem that requires you to complete the square, so you'll know that. So, but if you were doing a test or an SAT or something, you would not know that necessarily. Okay, so I'm going to leave my little blank here like we do, and that blank is to be completed, but we need to make sure we abide by rule number 2, or step number 2, which is to factor out an a if a is not equal to 1. So in this example, a was 1, but over here, a is 2. So before we do anything, we have to take the 2 out using GCF factoring. Okay, and then that is where we're actually going to complete the square. And notice I just kept an example that we had earlier. Half of 8 is 4, negative 8 would be negative 4, square would be 16. But see that whole process, you're going to take half of b, which is negative 8, and you're going to square it. So that would be negative 4 squared, and when you square something, it's always positive. That's an important thing to remember about math, about Algebra 2, is that squaring something makes a positive number. So you're going to add 16 here, but you have to be very careful about what you're actually adding here. You're not actually adding 16 here, right? Because this is being distributed, so that's not really 16, it's really 32. So you can either say 2 times 16 if you want, or you can just say 32, however your brain wants to deal with that. Okay, so to balance this out, this is negative 40 plus 32. That's going to come out to negative 8. So to balance the equation out, I have negative 8 is equal to 2. I'm going to go ahead and factor that. So that would be x minus 4, identical twin factor of x minus 4. And when you get better at completing the square, you're of course just going to want to write that as negative 4 squared, which is the process we need. So once we get to here, the question is, well, what do we do? Well, we're going to, if you look back at the steps, these steps are super helpful to have and understand, is we're now going to use method 1, the square root method, to solve for x. So I'm going to reverse Gelmdas. There is nothing to add or subtract over here, but there is something to divide. So we're going to start by dividing. Please don't ever distribute this. It does not have the same base or the same exponent, so it cannot be distributed. So over here we get negative 4. That, of course, cancels out. So we've completed the addition and subtraction, and then now the multiplication step. We're now going to square root. Don't forget that when I square root this, we have a plus or minus on it. So that's going to come out to, don't forget the square root of a negative is an I. This will come out to plus or minus 2i. And that's going to equal x minus 4. And then to finish it up, we are going to add 4 to both sides. And we'll get the same answer that we got earlier. Let's take a look at what that looks like. So we end up getting 4. Remember, the real part comes first, and then plus or minus 2i, the imaginary part. And that is equal to x. So if I go back and look at the, here at the same problem under the quadratic formula, I got the same answer, 4 plus or minus 2i. And here I got 4 plus or minus 2i. So you may say, why did we learn this process if we already have the quadratic formula? Some students like this process because it's very algebraic and it follows the steps of reverse Gelmdas, while using the quadratic formula is sort of, it's vague, and we'll never use a formula like that again in Algebra 2. So I need to teach you the quadratic formula so that you're able to, be able to do physics and other science subjects. But completing the square is the algebraic process, and that's an important thing to understand about it. So the other thing that completing the square can do is it can actually rewrite functions into from standard form, ax squared plus bx plus c into vertex form, which is really neat to connect this unit to the transformations unit. So the way that that works is you're still going to do the same thing, but instead of setting it equal to 0, you're going to set it equal to f of x or y equals. You're still going to want to have a space here. And remember, the reason it doesn't factor is there's no way to turn a 1 into a 6. So you want to remove this from the problem and put it over here so that the problem has room to complete the square. So we're now going to have f of x minus 1 is equal to x squared plus 6x plus that space that you've seen in the previous examples. And that space is going to be filled the exact same way. We're going to do b over 2, so 6 over 2 squared. And so that would be 3 squared, which would be 9. So we're going to put 9 here. We're also going to add 9 over here to balance the equation, so the algebraic property of equality. So we're now going to rewrite this as f of x plus 8 is equal to, we can go ahead and factor that if you want, and you might have realized that this factorization step is always going to be the middle term squared. I'll do it one more time, and on the next example I'll show you that you can kind of skip this step. So x squared plus 6x plus 9 will factor into x plus 3 twice. And so the final thing is to have f of x plus 8 is equal to x plus 3 squared. And you may say, well, how is that the same as the transformation unit? And believe it or not, in different places in the world, this is considered vertex form. But the way that we learn it, especially under Virginia State SOLs, and you might learn this eventually when you take pre-calculus, that this is a quadratic, and in that format, it's over there. So even in the United States, in pre-calculus, that format is a little bit more regular. But we know it like this: f of x is equal to x plus 3 squared minus 8. And if you remember from the unit on transformations, the vertex of this problem would be, remember, h is always opposite, so -3, -8. And you would graph your quadratic just to sketch that. -3, -8 is right about here. You would do 1, 1, 1, -1, 1, 2, 4, -2, 4, and then you would graph your quadratic. And we can easily access that on Desmos, which is what's cool. So let me show you the Desmos, and I will type it in. So we'll type in, you got to use y equals or f of x equals. I like to use y equals because it's easier. And then x minus 3 caret squared. I hit the right arrow key, minus 8. And you can see, I'll refocus that. Look at that, right? Oops, I made a typo. I put a minus there. So exactly like we did our sketch here, right? So it's pretty neat that and it's not even, if I were to be honest with you about why vertex formula is so useful, it's extremely useful for problems like that. And that is something you'll have to do in pre-calc and calc later. Now let's take a look at this one. So same situation, this problem doesn't factor because of this, but even if it did factor, to put it in vertex form, I still would want to move this over. Because remember, factoring is important for solving, but we're not solving this problem. We're trying to write it in vertex form. So you can use completing the square to get something out of vertex, put something in the vertex form, regardless of if it factors or not. All right, we're still going to use our little blank here, so plus a blank. Okay, but we have to factor that 4 out. That's the most critical rule to remember about all of Algebra 2, is that when you have a coefficient, you have to GCF. And that's consistent with when we learn transformations. So just keep that in mind. It's very consistent. Over here, this would just drop down. In fact, I'll just hold off for when we complete the square. So here we're going to complete the square by taking half of b squared. Nice little easy number. 2 divided by 2 squared would be 1 squared, and so the completed square here will be 1. However, the 1 here is not really a 1 because it's really 4 times 1. So you can either write 4 times 1 or just say it's 4, however you want to do it. So in the next step, we now have f of x plus 7 And then over here, we're going to have a 4 leading coefficient. That's really important. Thinking about unit 2, which is what we're replicating here, that is the vertical stretch, meaning that's going to make all of my output values 4 times larger. It's going to make a very narrow parabola. So this step right here, where you factor this into x plus 1 and x plus 1, once you get better, you can actually skip this step and just write x plus 1 squared. There's nothing wrong with doing that. And if you already understand that, please feel free to do it. And then here, we're going to need to move the 7 over. Again, in pre-calc, this may actually be standard form, so just keep in mind it's not as weird as it seems initially to us. But we're going to want to move that over so we have it in our H and K format that we're used to seeing. Okay, so here we go. And so this one would have a vertex at, right, don't forget H is always negative, so -1, -7. It's going to be very, very narrow because what happens is, if our vertex is here, instead of doing 1, 1, it's going to be 1, 4, -1, 4. Instead of doing 2, 4, it's 2, 16. It's like way up here. So let's take a quick look at Desmos for that one now. So if I were to type that one in Desmos, I would have y equals 4x plus 1 squared, right key over, oops, didn't square that one, right key over, and then -7. I like to just double check. I did make a typo just a second ago, so yep, it looks good. So notice it's way down here, and notice it even shows you, right, over 1 up 4 to get to that y-intercept. So very neat and nice way to check it on Desmos. In fact, if you wanted to, you could even type in the original problem to just correlate that you have the right thing. So that was y equals 4x squared. I'm just going to skip over here and look at it. Plus 8x minus 3. And you can see that it graphed over top of it. So that's that one. That's that one. Red is my answer. Blue is the question. I know I have it right. So, this is a process that really involves a lot of different moving pieces. So I wanted to make you a flow chart and go over some review questions about what would you do if you saw an assessment. So here's the flow chart. The first thing you do is determine if the bx term is missing. And if it is, use the square root method, otherwise known as reversing Gelmdas and taking the square root. Don't forget your plus or minus. If the bx term is present, I would always set the quadratic equal to 0 in an attempt to factor it using the zero product property. So you want to make sure your ax squared term is positive, and here are your 3 things you would do. Okay, the first thing you do is determine if you can use, if there's no c. So if you have bx, okay, and you have an ax squared next to it, you would be able to then use the GCF method. So an example of that is if I had 4x squared plus 12x equals 0. That's actually one of the problems the students have the most trouble with. You would just take out 4x, and then you'd have x plus 3, and then you would set each of those equal to 0 using the zero product property. The next thing you do, if c is present, meaning if you have a normal problem like x squared minus x minus 12 equals 0, meaning you have your c right here, you would try to factor it. And if it does factor, right, you would be done. But if it doesn't factor, you would either use the quadratic formula or completing the square. If you use the quadratic formula, you're going to use the discriminant first, right? And if you see at that point that you have a perfect square, oh, you made a boo-boo, you can go back and factor it. But if it doesn't, if the discriminant is not a perfect square, you have to complete the whole quadratic formula. So why don't we take a look at some examples. So when I look at number 1, the first thing I notice is there's no x. This is the easiest kind of problem. All you have to do here is solve for the square using reverse Gelmdas. So I look at this, I notice there's no bx term. Obviously there is one right here. So I would subtract 6, reversing Gelmdas. All right, and so I'm just going to run through that. This, of course, inverses out. Here we have -9. So I did the addition or subtraction at the bottom of reverse Gelmdas. Now I am going to divide. Okay, and I'm going to reduce that. That inverses out. So I'm going to reduce this over here, giving me 1/2. Now I will take the square root. Please don't forget that when you take the square root, when you have an equal sign, you have a plus or minus, and that will actually square root both the top and the bottom of that fraction. So don't forget that when you do this, you get plus or minus, right, the square root of 1, which is 1. Students forget that all the time. And then the square root of 2, which doesn't reduce. And then I have to do what I learned in geometry and earlier in this year when we went over radicals. I have to make sure that I then rationalize this by multiplying by the square root on the top and the bottom. So we get the square root of 2, and then on the bottom we would get the square root of 4, and of course the square root of 4 is equal to 2. So that would be the answer to this equation. So looking at this one, I have a different process because I have this bx term. So I'm going to set this equal to 0 and try to figure out what's going on. And when I look at this, which one of these is going to lead to me having a positive coefficient, lead coefficient. I want to move this 3 over to here so that my ax term is positive. That's super important. And that means I'm going to go ahead and move the 3 over here, and it actually will be in order over on the side. Okay, so these things inverse out. Here I have 2x squared plus 1x minus 3 is equal to 0. And keep in mind, when you have a lead coefficient that is not 1, you've got to still have to factor it. And the best way to do that is to actually use the box method. As we learned earlier, just we're going to use it in reverse. So the way you use it in reverse is you say, okay, to get 2x squared here, right, that's locked in, and this is locked in. And what we need to get is we need to get the middle term. So 2x squared is going to be made by using 2x and x. That's the only way to do that. And 3 can be made by, it's 1 times 3. One of them is negative, but you're going to figure that out in a minute. You don't figure that out at the beginning. That's one of the things that students do that gives them trouble. So we're just going to give it a try. Like, where would it make the most sense? So why don't we put the 1 here and the 3 here? So here we'll have 2x times 3, which is 6x. And here we'll have x times 1, which is x. And we need to subtract this. Is there any way to subtract these two to get 1? And the answer is no, because we simply put them in backwards. So, and that's a typical mistake. I actually did that wrong on purpose so that we could then see what to do. How do you get out of it? Well, you just erase it. And here you have 2x, right? 1 times 2x, and then x times 3 is 3x. And the question is, can we subtract these to now get 1? And the answer would be, yeah, if we subtracted them, this would have to be negative, right? Because negative 2x and 3x is 1x, and that negative lines up here, so that checks out, which means the negative originally was on the outside. So the factorization's right there. We have x minus 1, and we have 2x plus 3. And then we would use the zero product property to set both these equal to 0. X minus 1 equals 0. So x would equal 1. And then here we have 2x plus 3 equals 0. So we would have 2x is equal to negative 3, divide by 2, and we get x is equal to negative 3 halves. Please keep in mind that this could also be written like this using set notation. It's always in ascending order, so the negative 1 would be on the left side. Either way, you can write it like this. Technically, it needs to be in order, or like that. So, moving forward here, you're not going to want to get too frustrated. I want you to use the process of elimination. If your teacher has already given you a problem where there was no b and you took the square root to solve, and you had one where you factored, the next two are probably going to be completed the square or the quadratic formula, or maybe the GCF method, which sneaks in there. And sometimes your teacher's just going to tell you, solve this one with the quadratic formula and solve this one with completing the square. And the reason your teacher is going to tell you that is so that you are able to just demonstrate that you know how to. So these start off the same way as ones that, the only one you can start differently is if you don't see that bx term. So you're just going to start these the same way by setting them equal to 0. That is the same process, because when you solve the quadratic equation, you're still solving an equation quadratically, which is going to use the same process. So these will inverse out to 0. And then over here, we're going to have x squared plus 3x. Don't forget to combine your terms. 5x minus 2x is 3x. and then plus 7. And that clearly doesn't factor. There's no way to factor 7 into 3. So even if your teacher didn't tell you that, it was fairly obvious. So then we're going to do the discriminant first to just figure out, well, what's going on with this? Am I going to have imaginary or not? So b squared minus 4ac. And it helps to label. I'm just trying to go over some best practices with you to make sure you're doing a good job and not confusing yourself. A is 1, B is 3, and C is 7. Okay, so I'm going to now put those in here. It's good to use parentheses. So B is 3, so 3 squared minus 4 times 1 times 7. This is one we could probably do by hand. So this will just be 9. There's only one minus, so minus 7 times 1 times, 4 times 1 times 7 is 28. And then 9 minus 28 is negative 19. So that is going to clearly be two complex answers and have no x-intercepts. And the reason that's important is, your test might simply ask, again, which of the following has no x-intercepts, and this one would be the answer, and you would not have to solve or graph, you would just do the discriminant. So to complete the quadratic formula, you have x is equal to minus b, and then plus or minus the square root of b squared minus 4ac, but we already know that's negative 19, and then divided by 2 times a, which was 1. B, we'll go ahead and put that in here, right? So b is going to be 3, so it'll be negative 3. And we know from this unit and the previous unit that this is an imaginary number. And I'm actually now done because I get x is equal to negative 3 plus or minus I root 19. 19 does not break down. And then divided by 2. There's one last thing to do, which is to understand that this answer could be, you would divide this twice. So negative 3 halves plus or minus I root 19 over 2. And as we've mentioned before, there's a 1 here. Some people might say this is 1/2 I root 19 or something. All right, let's take a look at this one that's completing the square. If you know it's completing the square, then you only have to get rid of this middle term and put it over here. Because remember, completing the square is supposed to equal C. So if you know that it's completing the square, you can skip the step of setting it equal to 0 because I have C right here. And then this will inverse out. Here I'll have 6x. Here I'll have 2x squared plus 6x. And we'll want to include our space for the completed square. So I'm just going to move that over slightly. Put the 6x here. And then plus the unknown C value. Oop, got to be careful. We have a lead coefficient. We have to GCF that out. If you don't, the equation is not, you can't balance it. So you have to GCF that out. Okay, so there we go. And that is going to equal negative 10. So this one's a little bit more complicated than some of the ones we've seen, but I think at this point we can get through it. So we're going to cut b in half. It doesn't reduce. And square it, which will give us 9/4. Okay, so 9/4 will go here. But over here, we're going to add 9/4 times 2, which is really 9/2. So let's work through that. That to me is something that students have a lot of trouble with. So negative 10 plus 9/2. If you don't know how I did that, this will cancel with this, because remember, this is really 2 times 2. And just as I've shown you before, that 2 will cancel with one of those, leaving with 2 in the bottom. So the way I add this together, it's pretty easy to do. I just got to find a common denominator. So the common denominator here would be a 2. So I put it on the top and the bottom. So what I'm really going to be adding is negative 20/2, which is negative 10, plus 9/2. So that seemed hard, but it really wasn't that bad. It's actually negative 11/2. All right, so over here, we're doing the algebra work. So we have 2. And then, well, what do we factor this to? Remember that the factorization is always this. All I do is just write that down twice. So if you haven't seen that before, just go back and look at the other examples. It's always that number. This time it's a fraction, and other times it's been an integer, but it doesn't really matter. It's just whatever this is. This number is needed to balance this side, but this side is always this times this, because 3/2 times 3/2 is 9/4. And then we write it as a square. And for the first time, we actually have to write that down again because oops, sorry, 3/2. We have to write that down again because we hadn't finished with the arithmetic on that side. So now we're going to divide by 2. We're reversing Gelndos now. There's nothing to add or subtract, but there is something to divide. And this is the first time this may have happened. If you ever have a fraction divided by an integer, these two numbers simply multiply. And the reason is this is really 2 over 1, and then it reciprocates to 1 over 2, because if you divide by a fraction, you reciprocate. But you can remember that shorthand, that if you ever divide an integer by a fraction by an integer, you just multiply these. So it'd just be 2 times 2 is 4. And now you might realize why that was actually I know that fraction part was a lot, but that sure is going to be easy in this step, because here we're going to take the square root. We're going to square root this plus or minus, and the bottom is now the square root of 4. So remember, when we take the square root of this, we square root the top, the square root of negative 11. Oops. The square root of negative 11 will be plus or minus I root 11. And then the bottom, the square root of 4, is 2. And that's sure to make our life easier. And so then we have x plus 3/2, and then we subtract on both sides. And then you're done. And to do that, you would simply put it in front, kind of like we did here. They're different problems, as you can see. But this one, that's why that format for the quadratic formula is good to know, because it will always come out in that format when you use the square. And if you never practice with that format, when you do the quadratic formula, you think something's wrong when you do completing the square, even though you did it correctly. So you should be as fluid as I am after you do your homework. Just make sure that you try problems more than once, possibly. This is a chapter that is important for the whole year, and inside of every chapter in Algebra 2, there are quadratics. So spend your time now and review and review and ask questions and review.